let's take a look at 5.6. We're looking at systems of inequalities, which is going to lead us into some linear programming, which is a great application of these inequalities. Let's start with just some basic inequalities, and then we'll jump into the linear programming. To graph our inequalities, you have got to go back and remember how to graph all these different functions that we have graphed through the year. So you need to be familiar with graphing linear equations. This is a parabola, remember, and you can make notes over here if you need to, but ultimately, remember that your H and K are your vertex. So in this example, it would be a -4, -3. That would be your vertex. Remember that your A value is your vertical stretch. So on the parent parabola, from the vertex, you'd go over 1, up 1, over 2, up 4, over 3, up 9. But now you're stretching it vertically, so your Y values are always twice what they normally would be. Now, I'm not digging into re-teaching how to graph all these, so let's keep moving. Next one, be familiar with graphing a circle. This right here is a circle equation. You'll have an x squared and a y squared. Whatever is in here with your x is your horizontal shift. In here with your y is your vertical shift, and it creates your center point. So your center is HK. Always doing the opposite when you're inside parentheses. And then this is equal to your radius squared. So if I were going to graph this one, notice there's nothing with the x, so that means there must have been a 0 there. So my center point would be 0, 2. And then, since it equals the radius squared, it looks like my radius must have been 2. So from my center point, I would go up 2, left 2, down 2, right 2, get 4 points in there that I can draw a nice circle. Okay, square root graphs. Remember, they just look like this kind of a graph. This is your shifting. You're going to be going right 2, up 5. Log graphs. I don't know that I have a log graph on this one. In general, log graphs do this right here, where this is that special point at 1, 0. In our example here, it looks like it would just go, everything would go right 3. So that's your shifting. Okay, so just a quickie refresher of all these different functions we know how to graph. And what we're actually graphing, though, are inequalities. Inequalities are the ones that have less thans and greater thans in them. So here's sort of our process for that. The first thing you're going to do is you're going to just graph that function like we know how to do. But because it's an inequality, you're going to graph sometimes with a solid line and sometimes with a dotted line. A solid line means that your solution actually includes the function itself. Whereas if you show it with a dotted line, it does not actually include the function as actual valid solution points. Remember, solid is going to be when you have or equal to's, something like this. Dotted will not have the or equal to, something like that. Okay, once you have it graphed and you've decided on the whole solid versus dashed, then what you're going to do is you're going to use a test point to determine what part of your graph would have solutions that work and what part would then, if it works, then it would need to be shaded. So we use a test point. If our test point works, we shade in that space. If that test point does not work in the inequality, then we would purposefully shade away from that area. Let's try a couple. Now, on this first one, I know you know how to graph a line, but I thought I'd throw one in that had intercepts because that actually is a pretty handy method for graphing some of the graphs we do today. So remember the intercepts method. To find your x-intercept, you plug 0 in for y. If this was a 0, this whole term would go away. And so then you'd end up with a 3x. And remember, you treat it like an equation right now. It'd be a 3x equals 6. So that means my x-intercept would be at 2. So I put a dot right here at 2. And then we do it again. To find the y-intercept, you're going to plug a 0 in for x. And this whole term is going to go away. And ultimately, what I'd be looking at is this negative 2y. In your mind, you're thinking equals 6. So y would have to be a negative 3. All right, that's your intercepts method. Once you have 2 points, then I kind of like to get a few more just to keep some accuracy. I kind of eyeball what the slope is, and then I just keep it going a few times. So it looks like I'm going up 3 over 2, up 3 over 2. Now, do you feel like this line should be solid or dashed? All right, it has an or equal to, so we should be a solid line. Now what I'm going to do is do a quick test point. I almost always choose 0, 0 as my test point. The only reason I wouldn't is if my graph actually went through 0, 0, then you can't use that test point. So let's test 0, 0. If I put 0 in for x and 0 in for y, this whole mess would turn into just 0. And then I think, is 0 less than or equal to 6? Yes, it is. So what that means is that I want a shade on the side where 0, 0 is. All right, let's try another one. This next one is a parabola. The parabola has a vertex of negative 1, 3, and it has this little negative here, which is going to flip it upside down. So my vertex, negative 1, 3, and then from the vertex, I'm going to go 1, 1, but I'm going down, 2, 4, you're going down, put in your matching points here as you go, and we even have room for a 3, 9. Now, because this equation or this inequality does not have an or equal to on it, that means this is a dashed graph. So make it obvious that you're dashing this. And then I look and see if 0, 0 would be a valid test point. And it is. It's tucked inside it. My parabola is not hitting the 0, 0 mark. So let's put in 0, 0 and let's see how this works. I'm going to show the work a little bit here because this is a little bit trickier problem. But if I put 0 in for y, less than negative, then I'm going to put a 0 in for x. So it's 0 plus 1 squared, and then a plus 3. And this is really a question mark. Is it less than that? Let's kind of finish up this algebra on the right side. You'd end up with a 1 squared, that's 1, but then it's a negative 1 plus 3. Is 0 less than that? Well, that ended up being a 2. So yes, 0 is less than that, which means 0, 0 does work in the inequality. So I want to shade where 0, 0 is, which looks like it's inside this little parabola here. Don't shade it so much that I lose the dash on it. Make sure I can still see that it's dashed in some way. Okay, let's keep moving. The next level will be to graph a system of inequalities. And when you're doing a system of inequalities, you have multiple inequalities and you're shading and you're shading and you're shading. And so the solution set of this, of the system, I should say, of the system, oh, sorry, I didn't read that right at all. The solution is the set of blank. Okay, sorry. That would be the set of points that fall in the, I can't just say the shaded region. For it to fit in the system, it has to fall in the double shaded region. So wherever it got double shaded, but actually that's not even the right answer because look, I have 3 inequalities here. So that would be the triple shaded region. So wherever it gets shaded every single time is really the answer on that. All right, so let's look at what we've got for some equations. I tried to get you some trickier ones so we can practice. All right, on A here. Last time we did intercepts, so this one I'm going to put in slope-intercept form for us and practice graphing that way. I'm going to subtract the 6 to the other side. Oh, I lied. I'm not. You know what I'm going to do? I'm going to add the 2y. So when I add the 2y, it's going to make it positive for me. And I'm going to have this. So then I'm going to subtract the x and divide by 2. Now, if I had not done this, I would have ended up dividing by a negative. Don't forget that when you divide by a negative, that you have to flip the direction of your inequality sign. Okay, so this graph would have a y-intercept of 3, then I'm going to go down 1, right 2, down 1, right 2. Now, when I do this, I have to consider if I feel like this should be solid or dashed. It is not an or equal to, so this is going to be dashed. So I'm going to keep that going a little bit, get some points in there, dash this, and then I'm going to do my test point. I'm going to plug in 0, 0. Now you could do it in any version of these equations. I'll just keep it going because I have some space here. Is 0 greater than, when I put 0 in for x, that whole thing's going to turn into 0 plus 3. I do not think that's true. So that means I don't shade where 0, 0 is. And I'm going to shade the other side of my line. Okay, now let's look at the other inequality. This one has an x squared, so this is going to be a parabola. I would like the y to be isolated, so I'm going to divide by 2, and it's going to look like this. I would probably rather that be a 1/2 x squared less than y. I kind of like the y to be on the left. I probably would switch that around and say y is greater than 1/2 x squared. So when I graph this parabola, the vertex is going to be at 0, 0. But this is going to have a little bit of vertical shrink going on here because of the 1/2. So think through your table. Your parent table would be 1, 1, 2, 4, 3, 9, 4, 16. That's your parent table. But all of these y values are now half of what they used to be. So I'm going to go over 1 up a half, over 2 up 2. I'm going to jump right into the over 4 up 8. And then, because this also does not have an or equal to on it, I'm going to dash this graph. And I have to decide where I want to shade. This is one of those examples where the parabola actually goes right through 0, 0. So I don't get to use 0, 0 as a test point. I can use any other point that I want. Let's go ahead, and I think I'm going to plug in 0, 1. What if we just put in 0, 1? So if I put 0 in for the x and 1 in for the y, so I'd have a 1 greater than, putting a 0 in for x would get this right here, and 1 is bigger than 0, so I like it. I'm going to shade where that is, so I'm shading inside here. Now, you kind of want to shade lightly because ultimately the final answer is where it got double shaded, and I really need to be able to tell where that's at. So that looks like wherever I shaded green and blue. So it's this, and then this is up here, this is up here, and so it's kind of like this area right in here that got double shaded. And that's my solution. Okay, one more. This one's a little trickier. I've got 3 inequalities. Some of them are easy, some of them are a little trickier. And so I'm actually going to start with our easy ones, which are the bottom 2. This one right here, it only has a y, it doesn't have an x, so this is a horizontal line. I'm going to have a horizontal line at 0, and I'm going to graph all the y's that are less than that. So that's going to be underneath the line. So, and it is solid. Solid line, shading everything under. The third equation is actually just one of those V equations. It's an absolute value graph that went up 1. So if I go up 1, right here is the V. It's just your standard 1, 1, 2, 2, 3, 3. So I've got that. Same thing on the other side. I am doing a solid line because of the or equal to, and then I would do a test point. I could do 0, 0 because my absolute value does not go through 0, 0. So let's test that. Is 0 greater than or equal to the absolute value of 0, which is just 0, plus 1? And I would say no, that is not true. So what that means is I'm going to shade the opposite side of this. Now, the next thing I would do is I would shade this absolute value of x less than or equal to 3. That's actually kind of a tricky inequality. We haven't talked a lot about having it's an absolute value, but it doesn't have a y in it. So it's almost like it's a vertical line, except it has this absolute value. Here's really, that would break down into 2 possibilities. That would be x is less than or equal to 3, or it could be a negative x, that when I took the absolute value of it, then I got an x, and it was less than or equal to 3. If I divide by the -1, this is actually going to turn into an x is greater than or equal to 3. So I am looking for x being greater than or equal to 3 and less than or equal to 3. Those are 2 vertical lines. And they are solid lines. So I'd have this line right here. Maybe I'm going to change color so you can see it. And then I also have the vertical line here. So I'm looking at the values where x is less than 3. I'm sorry, I knew something was funky there. I couldn't think of what it was. When I divided by my negative x, that should end up a -3. That makes more sense to me. Okay, greater than -3, less than 3. That's everything inside here. But I really could have bailed on that. I just wanted to show you what that would graph like. But here's the thing. Where is this getting triple shaded? And the answer is nowhere. It is not getting triple shaded anywhere. It wasn't even getting double shaded after I was done with the first 2. I could have bailed there because there was no overlap at that point. It has to be triple shaded. It is not triple shaded anywhere. So this is actually what we would consider a no solution type of inequality, because I don't have any place that fits the category that I need. Now, I spent quite a bit of time reviewing how to graph those inequalities so that our linear programming could go quickly and we could focus on not the graphing so much, but the focus on the writing some of the equations. So linear programming, this is a method for finding a way to optimize. And so when we say optimize, I mean that we either want to minimize or we want to maximize one of those scenarios, some sort of a value when I give you some constraints. So I would want to minimize cost, or I want to maximize my profit. I guess would be an easy one. All right, so trying to optimize. But in the situation I have, I'm going to have what we call some constraints. And these are limits or restrictions on your variable. So I can't just do whatever I want. I'm going to have some restrictions. Now, when I graph all these restrictions, it's going to create what we call a feasible region. And the restrictions are going to be inequalities. And once you shade and shade and shade, you're looking for that double or triple shaded area, really maybe the quadruple shaded area. And it's going to look something like this right here. And the feasible region is the double, triple, quadruple shaded area, and it contains all the values that satisfy your restrictions. But more importantly, the optimization that I'm looking at will always happen at one of the vertices of your feasible region. So not only am I going to have these restrictions given to me, there is also going to be an objective function. And this is a function of the quantity that I'm wanting to maximize or minimize. Once I have the function given to me, so this looks like maybe this is some sort of a cost function maybe, and it's saying that the cost is equal to the 2x plus y. Now what I do is I look at my feasible region that I'm going to have graphed after I do all the restriction stuff, and it's creating these ordered pairs. So I'm going to list the vertices of my feasible region. So I see that I have a 2, 3. I have a 2, 6, 4, 6, and 7, 3. You list out all the vertices, and then what you're going to do is you're going to plug them in to your objective function. So I have a 2, and then I'm going to plug 2 in for x and 3 in for y. And that's going to end up getting me a 4 plus 3, so that's a 7. If I do the next one, I'm going to plug 2 in for x and 6 in for y. That's 4 plus 6, so there's a 10. All right, this one's a 4, 6. That's 8 plus 6, got a 14. And the last one, 7, 3. That's a 14 plus 3, so that's a 17. Now, depending on what I was trying to do, if I was trying to maximize the function, I'm looking for the one that gave me the biggest value. That'd be a 17. So my answer would be to maximize the function at 17, and that might have units to it. It might be $17 or something like that, but this one didn't have that. But at 17, then I need to do whatever the 7, 3 tells me to do, whatever that 7 and 3 represent. If I was looking to minimize it, I'm looking for the smallest number, so that would be minimizing it at 7. Then I'm going to use the situation where I have a 2, 3. All right, let's practice. Now that you kind of get the gist of that, let's practice writing some restrictions, some constraints from some sort of a situation. This is pretty lengthy, so I want you to, and I've given you an extra page to work with on this. You have this shoe manufacturer, and he's making outdoor and he's making indoor soccer shoes. Now, when he's making them, there's like this 2-step manufacturing process for both types of shoes. So each pair of outdoor shoes requires 2 hours of processing in step 1, and then 1 hour of processing in step 2. The indoor shoes require an hour of processing in step 1 and 3 hours in step 2. It's a lot of info right there. So on the next slide, I'm going to do it here because I can see all the numbers, but you're going to do it on the next slide. I just want you to create a little chart. That kind of represents what's going on. I have indoor shoes and I have outdoor shoes. And to make these, I have some sort of processing that in step 1, they're calling it, and then I have some sort of processing in step 2. And I'm just going to make a chart that kind of grabs all the key information. So 2-step manufacturing process, got it. Let's see, outdoor shoes require 2 hours in step 1 and 1 hour in step 2. So what I would do with that is 2 hours in step 1, 1 hour in step 2. Indoor shoes require 1 hour in step 1 and 3 hours in step 2. Now, those are kind of the constraints that I have. So it says the company has only 40 hours of labor available for step 1. So somewhere there's going to be a total column. And it depends on how you set your chart up. And there's not a right way or a wrong way. Sometimes you're going to be totaling to the side. Sometimes you're going to be totaling downward. This problem, it looks like the way I set it up, you have a 40 hours of labor available for step 1. So step 1 is going to max out here at 40. So I'm going to go downward. I'm going to make a total row and say step 1 maxes out at 40. And then if you keep reading, I have 60 hours available for step 2. So I'm going to max out there. And then it talks about, if we're not done yet, also outdoor shoes make a profit of $20 per pair, and indoor shoes make a profit of $15 per pair. How many pairs of each shoe should be made to maximize profit? Whew, finally I got to, what's the question here? The question is, I'm trying to maximize profit. So what I'm going to do is I'm going to write a profit function that's going to dictate how to maximize that. And so it looks like for my profit, so I'm going to call it a profit function, and it is actually dependent on two things. I'm going to call it X and Y. And you kind of have to tell me what's X and what's Y. So I'm going to say indoor shoes are X and outdoor shoes are Y. So when I write this, it says that outdoor shoes make a profit of $20, indoor profit of 15. So I would say 15x plus 20y is how I'm going to make a profit. That's going to be that profit function that I come back to. I still haven't even made a graph, and the graph is going to come from a bunch of other restrictions, and the restrictions that are created over here in this table. So what I get here is I get an equation or an inequality right here, and I get another inequality right here. But before I even write these inequalities, you have to remember what X and Y represent. These are how many shoes you're making. So we have kind of this, I call them like kind of gimme points, because I'm going to have these two constraints. X is going to have to be greater than or equal to 0, and Y is going to be greater than or equal to 0. I can't have a negative number of shoes. So this is going to force me into the first quadrant, but it is important to include it. It's like I said, gimme points. Write it every time. And then I have another inequality. It's going to come from this right here. 1x plus 2y, and I maximize at 40 possible hours, so that is going to have to be less than or equal to 40 hours. And then the other inequality, 3x plus 1y, is going to have to stay below 60 hours. And I end up with 4 different constraints, which means when I graph all of those, I'm going to end up with a nice 4-sided feasible region. So I'm going to end up with 4 vertices that I would then go back and test in this profit function. Now, right now, I'm just practice writing the constraints. We'll do the all-out problem here in a little bit. Let's just practice writing constraints. All right, so you have filled in the next slide with all this info. Let's keep moving. I've got another scenario. We're just practicing writing the constraints. I'll give you a minute. I want you to read through this on your own and then decide if you can figure out how to write your chart, how to fill in the info. Okay, sometimes I feel like it's easier. There's a lot of info here again. Sometimes what I want to do is I want to pick out the objective function first so that I can get those numbers out of the way. Those are not going to go in my chart. So you have to understand, what is the objective? What are we trying to do? Well, we are trying to maximize storage space. We want to be able to store as much as we can. So to maximize storage space, that is different than this right here. Floor space, that's not the same. It's like how much space are you filling up the floor for this? No, I want these cabinets to hold a bunch of stuff. So really, it's this right here, the storage capacity. This is part of my objective function. Cabinet B has a storage capacity of 18 cubic feet. So here's what I'm going to do. Now, it says A and B, but I'm going to really call it an X and a Y. And so my storage space, I guess I'm going to use an S function. It's respective to X and Y. So when I look at cabinet A, the storage capacity was 12 cubic feet. So I'm going to write 12X. And cabinet B had a storage capacity of 18 cubic feet. So that's how I'm going to maximize that storage space. This is going to be my objective function. That also means that I am not talking about storage capacity in my chart at all. So what that leaves then is it leaves money, which usually you think money is part of your objective function. It is not. Money is no object here. We're going to spend whatever we need to make sure we maximize our storage space. So when I'm making my chart, I'm going to squeeze it in down here. You're doing this on the next page, both of these things, next page. And I've got cabinet A, which remember we called X, and I've got cabinet B, which we called Y. And let's see what we can fill in. Ooh, I did not leave myself much room to write this, sorry. Cabinet A, okay, so I've got floor space. So I'm going to write here, this is floor space. You're doing it on the next page, so that'll work out better for you. And then I also have the cost. So let's fill in the chart. A requires let's even go back before that. The office has 60 square feet of floor space for the cabinets and $600 in the budget to purchase them. Those are going to be your restrictions. Those are your totals. So I have a total amount of square footage, floor space. I have a total amount of $600. I lied. Money is an object. I'm limited. So I'm going to have a total of $600. I have a total of 60 square feet. Cabinet A requires 3 square feet of floor space and costs $75. Cabinet B is 6 and cost $50. Now I'm going to write my inequalities. Here's one. Here's the other. Sorry, I got my Ring doorbell going off here. Okay. Don't forget the freebie points, but they're not freebie if you don't write them. X is going to have to be greater than or equal to 0. Y is going to be greater than or equal to 0. And then I'm going to write 3x plus 6y has to stay less than or equal to 60 because that's all the floor space I have. 75x plus 50y has to stay under $600. That's all the money I have. Again, those are your 4 constraints. We would graph them, find the feasible region, find the vertices, and then plug them into my objective function. Okay, one last problem. This one all out doing the whole thing. Let's take a minute to read it. Let's pick out what we feel like the objective is so we can write that objective function and get those numbers out of the way. Go ahead and read through it. All right, we are trying to maximize the number of people aided, which happened to be the last thing they talked about here. Each medical kit will aid 6 people, and the container of water will serve 10 people. All right, so here we go. I guess I'm going to do a S function again, serving people here with respect to X and Y. I'm going to go ahead and let medical supplies be X and bottled water is going to be Y. So when I talk about the medical kits serving people, okay, each medical kit aids 6 people. Okay, so that's 6X. When I talk about water, that's going to serve 10 people. So I'm going to go 10Y. That is going to be the objective function that I come back to later. Now I'm going to leave some space because I'm going to have some ordered pairs underneath that. I'm going to make my chart down here at the bottom. We've got medical supplies, and I've got water. And the restrictions I have is how big they are, because the plane is only so big. So this is your cubic feet of how big they are. But also when you're putting it in the plane, you have a weight restriction on them as well. So let's see what we've got. Each medical kit measures 1 cubic foot and weighs 10 pounds. Each container of water is also 1 cubic foot, but it weighs 20 pounds. That's going to be problematic. The plane can carry only 8,000 pounds. Okay, that's a total on the weight. 80,000. I think I said 8,000. And as far as space in there for cargo, we max out at 6,000. So now I'm going to write my constraint. I've got X has got to be greater than or equal to 0. Y is going to be greater than or equal to 0. Remember that we said medical kits are X, water is Y. So I'm going to have 1X plus 1Y has to stay underneath the 6,000 limit. And then I have a 10X plus a 20Y has to stay underneath the 80,000 limit. I need to graph these. I have 4 of them. I think I'm going to end up with a quadrilateral for my feasible region. When I do this, I could do X and Y intercepts, or I could do slope intercept form. Either way is okay. I'm going to do intercepts just to get a feel here for how big and what I need to be scaling by. On your homework, I'm nice enough to tell you exactly what you should be scaling your graph by so that it will fit on your graph. On this one here, I can see that both my X and my Y intercept needs to be 6,000. So I wouldn't want to scale by 1,000s for that because I'd be done right here and I'd have all this wasted space. Let's tell you what we have on this one. If you put 0 in for Y, this will go away and my X intercept will be 8,000. Okay. My y-intercept, if I put 0 in for x, oh, my y-intercept's only 4,000. Okay, so 8,000 is as big as it gets. So here's what I think I'm going to do. I'm going to go 500 is what I'm going to scale by. But I'm not going to write every 500. I'm going to go here, and I'm going to say that's a 1,000. I'm going to go here, that's 2,000, and keep it going. And then I'm also going to go up with the same scale. All right. Don't spend your time just watching me. I know, it's mesmerizing and all, but you should be doing this on your paper too. All right. Now, by doing this, I realize that this is forcing me always into the first quadrant. So I always just make this be the first quadrant, and this is always going to be 0, 0. But I still write them. All right, remember on this one that you're going to have 6,000 as your X and your Y intercept. So I'm going to be right here. Now, not only do you want to graph these, I cannot express to you enough how important making a neat graph is going to be, because you're trying to find these vertices, and if they don't cross nicely, you start guessing, and then it's wrong, and nobody likes that. Now, if your intercepts are both 6,000, then you have this nice slope of, well, it's going to be a -1. It's not a terrible idea to sit there and plot those points all the way down so that wherever the next one's going to intercept, you catch it. Because sometimes if you just draw the line, and I don't have a straight edge, you should 100% be using a straight edge for this, but I can't do that on a tablet very easily. So I'm just going to do my very, very best to make that straight. But on paper, you can use your straight edge. Now it is everything less than that, so I'm going to be shading downward. I'm not going to mess with the shading on this because I think it's going to get really cluttery pretty fast. All right, I'm going to change colors for this next one just to help us see where the difference between the two lines. Now, on this one, just for the sake of practice, I'm going to show you, well, maybe I'm going to do, instead of intercepts, even though I talked about it already, I'm going to put it in slope intercept form. So I'm going to do this over here on the right where I have some space. I'm going to subtract the 10x. And then I'm going to come through and I'm going to divide by 20. Oops, I missed that's a 20y right there. Divide by 20. That's going to be a -1/2 is what that's going to happen. And then I'm going to have a plus 8,000. No, I'm not. I'm going to have a plus 4,000 divided by 20. So I have a y-intercept at 4,000, and then I'm going to go down 1, right 2, down 1, right 2, down 1, right 2, down 1, boom, right there. Got it. That's going to be the intersection point. If you just draw these freehand and you're not extra careful like that, you oftentimes don't have a nice clean intercept point. So what I end up with, this is going to be my quadruple shaded area is in here. And so I have this point. That's actually another gimme point. I go ahead and give you points for this. I'm going to change up colors one last time. Over here, I'm going to put in all of my vertices. There are 4 of them. 0, 0 is one of them. Go ahead and write it. And then I have 6,000, 0. And I have a 0, 4,000. And then I have that spot where they crossed over here, which is 4,000, 2,000. Now, what I'm going to do is I'm going to take every one of those points and I'm going to plug it into the objective function. So when I plug in 0, 0, well, I'm going to get 0. I know it happens every time. It's fine. Go ahead and write it. The next one is 6,000, 0. So I'm going to be taking 6,000 times times 6. So that's 36,000 plus 0 in for y. That's just going to be 36,000. Now I'm going to plug 0 in for x. That's going to be 0. And 4,000 times 10, that's going to be 40,000. And this one may be a little trickier. You can use a calculator, but I like to use mental math when I can. 4,000 goes right here. 6 times 4,000, that's 24,000 plus 20,000. That's 44,000. So since I am looking to maximize the number of people aided, that looks like I look for the maximum number. That's going to happen right here. All right, so I'm going to circle it. You don't have to circle it because what I really want you to do is to write a sentence on what the heck that means. What did we figure out? Okay, so more than just, it does ask both. It says how many of each should be sent and what would the maximum number of people be that we're helping. So the sentence I would want from you is something that incorporates both of these answers and has units involved. And I have a little bit of room over here on the side, so this is where I'm going to write it. I'm going to say maximize the number of people aided at 44,000 by, what do we need to do to make that happen? Well, we need to send, it looks like 4,000. Remember, that's your X, 4,000 medical kits and 2,000 water containers. Nice sentence there explaining what the heck all this work meant. All right. A lot of work there. You can do this. Be neat, please. All right. Go get your homework done.